This is the second section of the probability generating functions chapter, and here we're going to be looking at the probability generating functions, or the PGFs, of standard distributions. Now, the distributions that we've met, the discrete distributions that we've met so far are binomial, Poisson, geometric, and negative binomial. Right, and each one of these has a probability generating function. So if we start first of all with binomial, so if you've got a binomial distribution and we know the parameters are n and p, then its probability generating function is given by this. So for example, if we had a binomial distribution with n was a third, no, it wouldn't be a third, that would be p. So let's say n was 10 and p was a third, that's more like it. Then our probability generating function, gx of t, would be 1 minus p, which would be 2/3, plus 1/3 t to the power n, which would be 10. Okay, and quite often we need to find these. We can't just use the result. We need to find them, but we need to make sure that it matches the result. Second one is if we have a Poisson distribution. So we know the parameter is going to be lambda. Well, this is the its PGF, probability generating function. So e.g., if we had a Poisson distribution, let's say where lambda was 4, then its PGF, gx of t, would be e to the power 4, and then in brackets lambda minus 1. Yeah, so just like before, we would need to find this. We can't just like plug the number straight into the results. Often we will need to find it in the question. Next comes a geometric distribution. Okay, so this one's a geometric distribution. So our random variable would be a geometric distribution, and we know that the parameter for that is just p. So e.g., if we had a geometric distribution where p was 0.3, then its probability generating function, its PGF, would be 0.3 times t over 1 minus, well then 1 minus p would be 0.7, so 0.7 t, so that would be its probability generating function. And then the last one is a negative binomial. So if our negative binomial, remember it can just be negative or NB for negative binomial. Our parameters are R and P. So e.g., if we had a negative binomial and R was 7 and P was 0.2, then our probability generating function would be P times T, so that'd be 0.2 T over, and then 1 minus, and then this is going to be 0.8 t, and all of this to the power of r, in this case, is 7. So there are probability generating functions for these standard distributions. Now, with all of them, just like before, with all of them, when t is 1, we get 1. Yeah, the sum of the probabilities is 1, just like before. Okay, an archer hits a bullseye with probability 0.6. She fires 3 shots at the target. the random variable x represents the number of times she hit the bullseye. Find the probability generating function for x. Now I've actually put it in that purple box there, but we're actually going to work it out from scratch. So the first thing to decide is what type of distribution is this? Well, she's got 3 shots at target, okay, and that's fixed, so it's a fixed number of trials. Trials are fixed, and that's fixed at 3. And we have a probability of success, and that is 0.6. So success P is 0.6. So when we have those, it's a binomial distribution, and it's telling us to use the letter X. So X is a binomial distribution with 3 trials, and a probability of success is 0.6. Now we could use the formula, but we could actually work it out much more quickly just by using like a little bit of common sense on this one and just working through it. So basically she's got these 3 shots at target. If X represents the number of times she hits the bullseye, well, she can either not hit it at all, she could hit it once, she could hit it twice, or she could hit it all 3 times. So let's work out the probability of each one of those. So let's start with 0. So if it's 0, it means that she misses the probability, or she misses the bullseye 3 times. So 0.4 to the power 3. If she hits the bullseye once, so there are 3 ways in which she could hit it once, either on the first trial, the second trial, or the third trial. So that means 3 ways of hitting once, which means 1 success, run out of space here, times 2 failures. You can probably see the pattern of the binomial here. Next one is the coefficient's going to be 3. Yeah, so it's like 1, 3, 3, 1 basically. So 2 successes, it means that 0.6 squared, that means 1 failure. And then 3 successes is only one way of getting 3 successes, so 0.6 to the power 3. Now I'm not going to work out what these are exactly. I will just sort of simplify them as I can, or I might even just leave them in the form they're in, because these now need to go into the probability generating function. So let's write it out in full first. That our generating function is going to be 0.4 cubed times t to the power 0, or just a number, plus 3 times 0.6 times 0.4 squared t to the power 1, plus 3 times 0.6 squared times 0.4 t squared plus 0.6 cubed t cubed. Now from this we can actually write it in the format which is basically this. It can look like that actually, because this comes from expanding 0.4, which is 1 minus p, plus 0.6 t to the power, so remember our probability of success is 0.6 to the power n, and that is in this case 3. And if we expand that, yeah, so this expanded gives us what we had in the previous step. Yeah, we need to learn how to spell expanded. So it's the same as what we get in that previous step. All we've done is put it into brackets and it fits the pattern, because this bit is 1 minus p, this bit here is p, and this bit here is n. Okay, example 4. X is a discrete random variable such that X is a Poisson distribution here, where lambda is equal to 1.1, show from first principles that the probability generating function of x is given by this thing here. So the first thing to point out, first principles, what does that mean? That basically means prove from scratch. Okay, prove from the limited information that you know about Poisson distribution. The same thing when you want to find a derivative from first principles, we start with the fact that we know how to find a gradient. That's what we start with. So what do we start with here? Well, we start with the way that we work out the probability of x for a Poisson distribution, and that is e to the power of negative lambda times by lambda to the power x over x factorial. Okay, so this is our starting point. Now, if we substitute x with 1 and then 2 and then 3 and so on, actually start from 0, don't we? Yeah, start from 0, so 0, 1, 2, 3 and so on, then we can work out the probabilities of each one of these using the formula. And we know that when we work out each one of those probabilities is going to go in front of either t to the power 0, t to the power 1, t to the power 2, and so on. Okay, I'll put those pluses in the wrong place. Let's try again. So it'll be a coefficient in front of t to the power 1 plus, that's more like it, t to the power 2 plus, and so on. So what we'll do is we'll work out each of those probabilities. So we'll start with working out the probability when x is 0. So that will be, remember lambda is 1.1, so that will be e to the power negative lambda 1.1 times by lambda 1.1 to the power 0 over 0 factorial. Let's work out probability when x is 1. So that would be e to the power negative 1.1 times by 1.1 to the power 1 over 1 factorial. And then 2. Yeah, this is going to be infinite, isn't it? Because with Poisson, it goes on forever. So we just want to write out the first few so we can see what the pattern is. So here I'm just working out the probabilities of these outcomes for Poisson distribution, and then these are going to be the coefficients of the t to the power 0, t to the power 1 and so on. So what we'll do, we'll simplify each one of these. So this one, well, we're basically timesing by 1 and divided by 1 because 0 factorial is 1. So we just end up with e to the power negative 1.1. Here we'll do the same thing here, dividing by 1 factorial, so we effectively divide by 1, so here we just end up with 1.1 e to the power negative 1.1. We'll do the same here. Here we'll have 1.1 squared e to the power negative 1.1 over 2 factorial. Notice I'm not working out the factorial or squaring out the top part because that's going to help me in the next part. So we'll just realise that power there should be 3. So 1.1 to the power 3 e to the negative 1.1 over 3 factorial. Okay, so our probability generating function is going to be the sum of all these probabilities. So the first probability, e to the negative 1.1, and that goes in front of t to the power 0 plus 1.1 e to the negative 1.1 t to the power 1 plus 1.1 squared e to the negative 1.1 over, that's 2 factorial, t squared plus, I have to write it down here, 1.1 cubed e to the negative 1.1 over 3 factorial t cubed, and so on. So we could probably work out the next one's going to be 1.1 to the power 4 e to the negative 1.1 over 4 factorial t to the power 4. So we know this goes on forever. So the next step, we want to find out what the sum of this infinite series is. Sum of infinite series. Right, so can we factorise anything out? Yes, we can. E to the negative 1.1 can go outside the bracket, and then in the bracket I'll dispense with t to the power 0 because that's basically 1, isn't it? So I'll put 1 plus 1.1 t, or t to the power 1, plus 1.1 squared over 2 factorial t squared. So all I'm doing is factorising out the e to the power negative 1.1. Okay, plus like that. Right, so the bit we're interested in is this part here. I'm going to find the sum of that. Now you may recognise the bit in the bracket, so you may recognise this bit here, and you'd be right in thinking Maclaurin series. Now let's just remind ourselves of a Maclaurin series that looks like that, and actually the Maclaurin series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. Now that sort of matches up. If we make x equal to 1.1, we get that series there. So this is basically that Maclaurin series, but with 1.1. So you could think of it as 1 plus 1.1 t, and then you've got your 1.1 squared t squared. So in fact, sorry, we can think of x as being 1.1 t, not just 1.1. So 1.1 t, if we replace x with 1.1 t in this Maclaurin expansion, we get this. So basically that bit in the brackets, this bit here, all of that we can think of as e to the power 1.1 t. That's the bit in the brackets. That was times by this that was factorised out, e to the negative 1.1. So this is our probability generating function here. Yeah, and we used the formula for finding the probability for a Poisson distribution, and we also used the Maclaurin series to simplify that bit in the brackets. So we've actually now got our probability generating function. There's one more bit to do, because if we look at the form it's in, so I'll just highlight it up here. Can you say it says e to the power lambda, and then in brackets t minus 1. Now what does that mean with what we've got here? Well, it means I need to get rid of the red box because I haven't quite finished. So our probability generating function. Now when we've got powers and we multiply them together, we can add them together. So you could say this is the same as e to the power negative 1.1 plus 1.1 t, and then from there we can factorise it and put the 1.1 outside, which is lambda 1.1 and then in brackets we'll have t minus 1. So we've proved that from first principle. So my red box actually should go around this. Yeah, that's my probability generating function proved from first principles. Okay, so a tetrahedral dice, that's a 4-sided dice, is rolled until it shows a 4. Okay, so 4 sides. If it's fair, that means the probability of getting a 4 is going to be a quarter, and it's rolled until we get a 4. The discrete random variable x represents the number of rolls up to and including the first instance of a 4. Show from first principles that the generating probability function for x is given by this expression here. Now the first thing we need to do is to identify what type of distribution this is. Now because we are carrying out trials until we get success, it's a geometric distribution. So geometric distribution, the features are going to be basically trials until, let's write this out in English rather than some gobbledygook, trials until success, okay, and then stop at success. Yeah, if you see these features, and there's only going to be one success, and so trials until one success. Yeah, it's only going to be one success, all the rest are failures. But when you get that success, you stop. It's a geometric distribution. So our random variable is distributed as a geometric distribution with p as a quarter, and we want to get to this at the end from first principles. So if we're doing it from first principles, the very first thing that we need to do is to write down how we get the probability for a particular outcome with a geometric distribution. So a geometric distribution is going to be one success, yeah, and then x minus 1 failures. So it, you know, if it's going to be 10 rolls of the dice and you get success on the 10th roll, then you're going to have 9 failures. Right, so what we're going to do now is to work out the probability of x equals 0, x equals 1, x equals 2, and so on. Now if we start with x equals 0, you'll see we'll run into a problem. What does this mean? It means that you don't roll the dice. On no rolls you get a 4. No sense. Okay, so we can't start with 0 because that doesn't make any sense. How can you have no rolls of the dice and get a 4? You're going to need at least one roll of the dice. So unlike other distributions where it can start with 0, geometric, in this particular example, we need to start with one success, or at least one roll. So basically you get the 4 on the first roll of the dice, which means that probability is just going to be a quarter. Okay, right. What's going to happen if we need 2 rolls of the dice? Well, that means that we get one success, we get one failure. What if it takes 3 rolls of the dice? Well, we're just using the formula here as well. So, so there's my p. Here's my 1 minus p. But now it's going to be to the power 2. I suppose for the previous one I could have put to the power 1 here, and here I could have put to the power 0. Yeah, but we can think of it in like a common sense way without even using the formula. So if I was to do a common sense way without using the formula, I say, right, I'm going to have one success. That's going to be on the 4th roll of the dice, but the first 3 are going to be failures. Okay, and so on. Now this should be enough to help me get my probability generating function. So let's write this down. So we're going to take each one of these values and put them in front of our but they're going to be the coefficients of t to the power 0, t to the power 1, and so on. Right, now because there was no t equals or x equals 0, there's nothing to go in front of t to the power 0, so there's no number there. The first one we're going to have is going to be a quarter in front of t, or t to the power 1. The next one is going to be a quarter times by 3/4 in front of t squared. Now notice I don't multiply these fractions out because I want to keep them like this, because I want to find patterns. Next one, 3/4 squared t cubed, and the next one a quarter times by 3/4 cubed t to the power 4, and so on. So this is an infinite series. Right, let's factorize it out. Now what can I take it as a factor? A quarter t. So take a quarter t out as a factor, then I'll have 1 plus 3/4 t plus 3/4 squared t squared plus 3/4 cubed t cubed plus dot dot dot, because this goes on forever. Now what I can do, where I've got like 3/4 squared t squared, that can go together. So I'll have 1 plus 3/4 t plus 3/4 t all squared plus 3/4 t all cubed, and so on like this. Now I can find the sum of this, because this is a geometric series or a geometric progression, and the sum of an infinite geometric progression is the first term divided by 1 minus the common ratio. So in this case the first term is 1 and the common ratio is 3/4 t, because to get from one term to the next we times by 3/4 t times by 3/4 t. So because it's an infinite series, we can find the sum of that. Now I don't know what's happened to this 4 in my 3/4. Let's do that again. We can find the sum of that. So let's do this over here. So we'll have equal a quarter t, and then times by the sum of that. So the first term is a, which is 1, over the common ratio, which is going to be 1 minus 3/4 t. And by putting the quarter t at the top of that fraction, I've got my probability generating function in the form that I want. So I'll have a quarter t at the top over 1 minus 3/4 t. Now if we compare this with the form of a probability generating function for a geometric distribution, you'll see you'll have probability of success times by t, which is what we've got at the top here. Then we'll have 1 minus, and we've got 1 minus. Then it's the probability of failure times by t, and which is what we've got here. And we've proved this from first principles. So first principles is you basically start with the formula that gives you the probability for each individual value of x. So here we have a discrete random variable, which is a negative distribution, negative binomial, and we need to prove from first principles So that actually means using the formula that gives us the probability of each individual outcome, which is this, I believe, pretty sure this is in the formula book, and then q to the power x minus r. So it basically means using that to get to this. Okay, so it's the same as that. And then it says we can quote this result without having to prove it. That's because it's unlike the other distributions where we can sort of write each term out and add them together. We can't really do that with this, because to get each probability, as we've just written out above, we need to do this. Yeah, and that's going to be tricky to do. But what we do know is that when x is 1, that will be the coefficient of t. When x is 2, that will be the coefficient of t squared. When x is 3, that will give us the coefficient of t cubed, and so on for our probability generating function. And our probability generating function is going to be the sum of these. Okay, so we need to find the sum of this infinite series. So let's do that. So our probability generating function is going to be the sum of, from x equals r to infinity, of each one of these coefficients of t to the power x, yeah, because then x is 1, x is 2, or x starts from r, and so on, up to, and then r plus 1, r plus 2, and so on like that. To help us simplify this, what we're going to do, we're going to take this t to the power x, and we're going to write it as t to the power x minus r times by t to the power r. Now that is the same as t to the power x, and the reason we're doing that is because look at the powers. That means we can start putting things together and simplify them. So the next step, we will have so the sum of x equals r to infinity, then we've got x minus 1, r minus 1, and then p r t r, so this is where I've split the t up, and then q x minus r t x minus r. So all I've done is taken those two terms, okay, and I've just put them here like that. So basically those two together just make t to the power x, and the reason why I've done that is because I can now put together those terms. So here I've got x minus 1, r minus 1. So here I'll now have pt to the power r, and then qt to the power x minus r, like this. Now from here I can take this term and I can place it on the other side of the summation, because this term is independent of x. So as x changes, that term there won't change. So as x changes, because there's no x in it, okay, as x changes, this term stays the same. So it's like a constant. So what we're going to do now is bring that to the other side of the summation sign. So we'll have pt all to the power r, and then we want the sum from x equals r to infinity of this x minus 1, r minus 1, and then qt to the power x minus r. Right, now we're ready to use this proof here. The only difference is where we've got q, we'll put qt. So we're going to use that proof, and maybe I'll write it down. So here we're just going to say something like since our sum of x equals r to infinity of x minus 1 r minus 1 of q to the power x minus r equals 1 minus q to the power of negative r. So this is a result that we can use. So since we have that, then what we can do is use that proof and use, whereas this is q here and q there, we will put qt. So we're now ready to write down our next step, which is going to be pt to the power r, so that was in front of the summation, and then the sum of all of this stuff here, we're using the result that we can use without having to prove it. That will be 1 minus qt to the power negative r. Now that's the same as pt to the power all to the power r over 1 minus qt to the power r. Now the power r can be taken out, and we're also told in that proof that we've used that q is 1 minus p. So our very last step is going to be to take that power of r outside the whole thing and replace q with 1 minus p, and then t there, all to the power of r. So we've proved that statement as required. So out of all the proofs, probably the one that's that's the trickiest to do, but there's a couple of points in the proof that if you can remember them, like changing the t power up here, changing it to x minus r and t to the power r. So if you look at these powers and think, right, I want to write t as these powers, that's an important step. That will then allow you to factorize it. The next important step is realizing that for any particular question this is constant, so that's going to go over to the other side of the sign. And then literally when we get to that point, when we get to here, this is when we can use the result and just substitute q for q minus t. So we get this result here. Obviously negative power means you can write that at the bottom. Back to the proof again, it says q is 1 minus p, so we can do that, and we've got our result at the end. So this is worth practicing a few times until you can sort of do it without really having to think too much about what you need to do as you get through each step. Okay, so you should now be able to do exercise 7b on pages 134 to 135, and I've got listed here the different probability generating functions, and you may be required to prove those from first principles. So what I'm going to do is just pause and write down the first principles statements you're going to use to start you off in these proofs. So here you have the different formulae for the binomial, the top one, Poisson, second one down, third one down, geometric, and then the bottom one, the negative binomial, with in blue the proof or that statement which you can use without proof in the exam.